All right, it's time to do some integrals with trig functions again. So there's some particular tricks that I want you to kind of see so you know when to use them. And it's when it involves powers of trig functions that pair up nicely. We're trying to use some kind of a u substitution here so we can integrate just a power function, but it's not always clear how to set up the derivative. So I'm just going to give you three examples so that you can kind of see how to set it up. We're going to start with the first one up here over here. We have sine to the fourth cosine cubed. When you have sine and cosine, what you really, really hope for is that one of the two has an odd power. Because if there's an odd power, that means there's going to be one left over when you change cosine squares into sines. And we can change cosine squares into sines by solving this and substituting cosine squared equals 1 minus sine squared. So that's going to be our setup here. We're going to change two of those cosines into sine squares, and then that'll leave us with a power of sine and just a cosine to let us do a nice u substitution. So let's go ahead and do this first one. So we're doing the integral of sine to the fourth of x times the cosine cubed of x dx. So our first step is going to be to just pull out one cosine out of this. And I'm going to pull it out all the way on the right because I want that to be part of my derivative. So I want a cosine x dx at the end. So I'm going to have sine to the fourth of x, cosine squared of x, and then cosine of x dx. So I still have three, right? I still have cosine squared times cosine. That's still cosine cubed. But now my cosine squared, I'm going to replace by 1 minus sine squared. So I'm going to get the integral of sine to the fourth of x, 1 minus sine squared of x, and you need the parentheses here, times cosine of x dx. And now I am pretty much set up to do my u substitution. So I'm going to let u equals the sine of x. And the reason I want sine here is I have my cosine here already to be the derivative. So du, which we do by taking the derivative of u, so we're taking the derivative of sine of x, which is just cosine of x, and the dx. So remember, this is really du dx, but I'm just putting the dx over there. And now I can just go ahead and resubstitute back. Every sine becomes a u, and cosine x dx becomes du. So I just get the integral of u to the fourth, 1 minus u squared du. We can multiply this out to just do two power rules. So this will be the integral of u to the 4 minus u to the 6 du. Great, it's just power rules. So to integrate a power, you up the power by 1 and divide by that newfound power. So we get u to the 5 over 5 minus u to the 7 over 7 plus c. And now because it was a u substitution, at this point we have to go back to our original x in order to get an answer. So u is sine of x, so we just back substitute. Sine to the 5th of x over 5 minus sine to the 7th of x over 7 plus c. And that does it. We have our full integration. So again, the trick is we take the odd power that's left, pull one out to become the derivative, and everything else becomes the other function. And then we do our u substitution and integrate. Works great. Let's move on to how to do this with secant and tangent. So secant and tangent behave a little bit differently because secant and tangent have different looking derivatives, right? If you take the derivative of tangent, that's secant squared of x. But the derivative of secant x is secant x tangent x. So if you have a bunch of even powers, you can let your derivative be 2 of the secants, which is what we're going to do here. So our u is going to be tangent. But if you have both that are odd powers, then you want to be able to factor one of them out. Or actually, as long as they're both the same power, really. But you're really going to need both of them to be odd because you need to have what's left of of tangent be able to transform into secant to pull out a secant times tangent. So this one we're going to solve using the first one, and this one we're going to solve using the second one. So let's set up the tangent to the squared secant to the fourth dx. All right, so our trick here is we're going to pull out a secant squared to play the role of the derivative. So I'm going to have secant squared x dx on the far right. And I'll have tangent squared x, secant squared x, secant squared x dx. And this here is going to be my du. And that's going to be the derivative of tangent, which means I need everything else to become a tangent. Fortunately, I can transform secant squared into tangent squared plus 1. So I'm going to start by doing that. So I have the integral of tangent squared of x times the integral of tangent squared of x plus 1 times secant squared of x dx. And now my u substitution is set up. I'm going to have u as tangent. Du will be secant squared of x dx right here. And so my integral just becomes the integral of u squared plus 1 du. Again, now we multiply out and use the power rule. So integral of u to the fourth plus u squared du. Integral of u to the fourth is u to the fifth over 5. Integral of u squared is u cubed over 3. And we back substitute to get our final answer as u as tangent. So tangent to the fifth over 5 plus tangent cubed over 3 plus c. So this is the antiderivative of tan squared x, secant to the fourth x dx. So it feels very much like the last one. It's just that the setup is a little bit different. For the last one, we can't use tangent because we're not going to have an even power of secant left over after transforming. We have just one. So we have to go the other way. We're going to use secant times tangent as our du setup. So let me show you how to do that, and that'll end this video. Let's go ahead and integrate tangent cubed x, secant cubed x dx. So the first thing we're going to do is we're going to pull out both a tangent and a secant. So I have my secant x, tangent x dx, and this is going to play the role of my du, which means I want my function that I take as the derivative to be secant. So I need tangent to be transformed into secant. Tangent squared is going to be secant squared minus 1. So I'm going to replace tangent squared by secant squared x minus 1, multiplied by secant squared x, multiplied by secant x tangent x dx. And now I'm ready for my u substitution. U is going to be secant x. Du will be secant x tangent x dx. And so I get the integral of u squared minus 1 times u squared du. Multiply out, integrate. Integral of u to the fourth minus u squared du. And now to integrate, we do the power rule. U to the fifth over 5 minus u cubed over 3 plus c. And when we back substitute this time, u being secant, we get secant x to the fifth over 5 minus secant cubed of x over 3 plus c. That's pretty much it. That's all the tricks I wanted to show you for this. If those tricks don't apply, you kind of get stuck in a place where you're going to have to do both substitution and use a different power to get rid of the squares. So you'll end up doing a half angle type formula. You'll just proceed, but it's going to get a little bit messier, a bit longer. So we're not going to really worry about those in what we're doing today. So have a great day, and I'll see you in the next video.